There is a building in the Middle East that stands on nothing, no bedrock, no hillside, no inherited plot of land passed down through a city's history, just open water. And then, 5 years later, 321 meters of steel, concrete, and sail-shaped fabric rising out of it. If you're an American viewer, picture this. It's like building the Empire State Building on a sandbar you made yourself in the middle of the ocean, with no bridge, no roads, no power grid, nothing but boats and buoys marking a spot where the Arabian Gulf used to be the only thing around for miles. That's not an exaggeration, that's literally where this story starts. This is the story of the Burj Al Arab, the Tower of the Arabs. The building most people have seen 1,000 times in photos and have almost never seen the real story behind. Not the marble, not the gold, the part before any of that, the part where a team of engineers had to invent the ground itself. If you've ever scrolled past a photo of this hotel and filed it away as shorthand for over-the-top luxury, you've only ever seen the finished product. The sail-shaped silhouette glowing at sunset, the gold-leafed atrium, the helipad hanging over open water. What almost nobody sees is the part of the story that made any of that possible. 3 years of marine engineering just to create solid ground, followed by 2 more years of construction most people never think to ask about. Compare it to something more familiar. When engineers built the Golden Gate Bridge, they were anchoring cables to land that had existed on both sides of the strait for millions of years. When crews poured the Hoover Dam, they were building against a canyon wall that wasn't going anywhere. Almost every major foundation project in American engineering history starts from the same basic assumption: there's already ground to build on. This project didn't get that assumption. It started as a set of coordinates marked with floating buoys over open water and nothing else. Part 1. A picture before a place. In 1993, Dubai was not the skyline you know today. There was no Burj Khalifa, there was no Palm Jumeirah. Dubai was an ambitious port city on the edge of the Gulf, trying to figure out how to get the rest of the world to notice it. Sheikh Mohammed bin Rashid Al Maktoum, the ruler who would go on to reshape the entire city, had a specific and almost stubborn idea. He didn't want a hotel, he wanted an image, something so singular that a person in London or Tokyo or Los Angeles could see one photograph and instantly know that's Dubai. Before they knew anything else about the place, they'd know that shape. The man who gave him that shape was a British architect named Tom Wright, working for the firm Atkins. Wright didn't design a rectangle with rooms in it. He designed a sail, specifically the sail of a dhow, the traditional wooden boats that had been fishing and trading along the Arabian coast for centuries. It was a shape with real cultural roots, not just a piece of eye-catching geometry. And in 1993, it existed only as a sketch. Turning that sketch into a building meant solving a problem that had nothing to do with architecture and everything to do with geography. There was no site, not no site yet in the sense of needing permits. There was no land. The location Sheikh Mohammed wanted, 280 meters of Jumeirah Beach, was simply sea. So before Atkins engineers could think about steel or glass, they had to answer a much stranger question. How do you build the ground under a 321-meter building from scratch in open water? Part 2. Building the floor of the ocean. July 8, 1994, the site was marked with nothing more than a ring of floating buoys. No pilings, no platforms, no equipment yet in place, just open water where, 3 years later, a foundation would exist. It's worth sitting with that image for a second. This entire structure, the one that would become one of the most photographed buildings on Earth, began as a set of coordinates floating on the surface of the Gulf. A pile-driving barge anchored over the seabed, and crews began rigging a hydraulic hammer. The plan called for 230 piles, massive concrete columns, each one 40 meters long and about 1.5 meters wide, driven straight down into the sea floor. Here's the part that separates this project from almost any other foundation job on the planet. Engineers went looking for bedrock, and there wasn't any within reach. Solid rock sat more than 180 meters below the surface, far too deep to design around, which meant the piles couldn't rely on hitting something solid and stopping. Instead, they had to be driven so deep and gripped by so much compacted sand along their entire length that friction alone would hold the building up. Engineers called these friction piles. In practice, it meant the entire weight of a 130,000-ton concrete and steel tower would eventually be supported not by rock but by the sheer grip of packed sand clinging to concrete columns. 2 rigs worked at once to keep the schedule on pace, hammering pile after pile into the seabed, each one load tested before being trusted to carry weight. Around the emerging forest of pile heads, crews installed temporary steel sheet piles, a kind of retaining wall, to hold back the sea while the real island took shape inside that boundary. Along both edges, workers dropped rock, and for the first time in Gulf construction history, precast concrete armor blocks shaped specifically to absorb and break up wave energy rather than simply block it. It was borrowed thinking from coastal engineering used to protect breakwaters, applied here to protect a building site that didn't exist yet. By the time the last of the 230 piles was driven, the ocean floor at this spot had been completely rearranged, but there was still no island, just a hidden skeleton of concrete columns sitting under open water, waiting for land to be poured on top of it. Part 3: Making land where there was none. This is the stage most people never think about when they look at a photo of the Burj Al Arab, because by definition it's invisible in every photo. The island itself had to be manufactured. Crews pumped a slurry of sand and water, called hydraulic fill, into the space between the sheet pile walls, displacing the seawater bit by bit. Workers checked the fill level every single hour because the margin for error ran in both directions. Pump too fast and the pressure could buckle the retaining walls. Pump too slow and the whole project would fall behind a schedule that had almost no slack in it. Over the following weeks, the slurry settled and the water drained away, and for the first time since anyone had marked this spot with buoys, there was land, not stable land yet, just wet, loose sand recently plucked from the seabed. Loose, saturated sand can't support a skyscraper any more than a sandcastle can, so crews drove vibratory compaction probes into the new fill to force it into a dense, load-bearing mass. Only then did the protective layer go on, large armor rock across the surface, followed by a ring of precast concrete honeycomb blocks around the island's edge. Again, a first for the region, engineered so that incoming wave energy would bleed through the structure instead of slamming into it directly. The seawall that resulted rises 7.5 meters above sea level, tall enough that the hotel's lowest floors sit safely behind it, designed to withstand what engineers call a 100-year storm. A storm so severe statistically that it's expected to occur only once a century. 3 years of marine construction produced in the end a stretch of solid ground exactly where there had been open Gulf water, an artificial island built specifically there and only to hold up one building. Part 4: The Raft. With the island formed, engineers had one more foundation problem to solve before a single wall could go up. How do you connect 230 individual piles into a single structure that acts as one unit? The answer was a raft foundation, essentially one enormous continuous concrete slab tying every pile together so that the load of the entire building would be shared evenly across all of them rather than concentrated on whichever pile happened to sit under the heaviest point. Before the raft itself, crews trimmed every pile head to the exact same elevation, each one cut to within 5 millimeters of the design height because the giant slab above needed a perfectly flat surface to sit on. Then came a layer of blinding concrete, a working floor poured directly onto the compacted island to give workers stable footing and protect the layers above. Over that went a heat-welded waterproof membrane because for the next 100 years, the Gulf would be trying to force water up through this exact spot. Then came the rebar, hundreds of workers hand-tying steel reinforcement across the entire footprint of the raft, wrapping cages around every pile head so the load transfer between pile and slab would be as strong as the concrete itself. And then the pour, 70,000 cubic meters of concrete placed in a single continuous operation. This wasn't a project where you could pour half of it, take a break and finish the next day. A stoppage would create what's called a cold joint, a seam where two separate pours meet and never fully bond, creating a permanent structural weak point. So the pour ran straight through, day into night, vibrators working through the pour to eliminate air pockets that could become hidden voids under the building's full weight. Concrete generates its own heat as it cures. Enough heat on a mess this size to crack itself apart from the inside if left unmanaged. So engineers cast a network of cooling pipes directly into the raft, running cold water through them for weeks to keep the internal temperature under control, while crews covered the surface with wet burlap to slow the drying process and prevent surface cracking. Calculated joints were cut into the slab to let it expand and contract safely with temperature changes over the decades ahead. 70,000 tons of concrete sitting on 230 piles in the middle of the Gulf, and the hotel itself hadn't started yet. This was still just the foundation. Part 5. The core rises. Once the raft cure, column starter bars were set into it, positioned from a precise building survey grid, and the entire slab received an epoxy coating meant to resist a century of salt water exposure. Only then did construction begin on the part of the building people actually associate with a skyscraper, the core. Engineers used a technique called jump form construction, a system of formwork that essentially climbs the building as it's built, floor by floor, with no scaffolding required from ground level all the way to the top. Crews poured the central concrete core, let it cure just enough to bear weight, jacked the formwork up to the next level, and poured again. Table forms, large horizontal platforms, each about 18 meters long, hung directly off the completed walls rather than being propped up from below, then flew by crane to the next floor once a pour was done. Structural engineers at Meinhardt International had re-engineered the floor system to use post-tensioned concrete, steel tendons threaded through ducts cast into every slab, then stressed, pulled to a precise tension after the concrete cured. The effect is that the slab essentially squeezes itself into permanent compression, allowing thinner floors and faster construction cycles than a conventional reinforced slab would allow. That cycle: pour, stress the tendons, strip the forms, fly them up, pour again, repeated 56 times as the core climbed toward the sky. By the time it reached roughly the halfway point, the building's signature silhouette, the curved sail shape, was already visible from the air. Even though the actual sail hadn't been installed yet, the mast was reading true before the fabric ever arrived. At around 250 meters, workers were pouring the final sections of core wall, with the Gulf stretching 400 meters in every direction and nowhere to retreat to if something went wrong. When the last core pour was finished, the concrete spine of the building stood 321 meters above the sea. 130,000 tons of raw structure balanced on those 230 piles, still completely unclad, with no glass, no gold, no marble, just the bones of what would become one of the most recognizable buildings on the planet. Part 6. An exoskeleton over the sea. Most skyscrapers hide their structural steel behind a facade. The Burj Al Arab does the opposite. Its steel frame is worn on the outside, an exoskeleton that gives the building both its distinctive silhouette and a huge share of its actual strength. 9,000 tons of structural steel arrived by barge, and crews began bolting the first beams to anchor plates that had been cast into the core walls months earlier. Connections positioned with enough precision that there was no room for adjustment later. Every bolt was torqued to exact specification because this frame wasn't decorative. At 300 meters up, wind loads on a building this shape and size are enormous and constant, and the exoskeleton exists specifically to carry that lateral force. To do that, crews installed diagonal cross-bracing across the frame, steel members that dramatically increased the structure's stiffness with every brace added. 2 iron workers would bolt each brace simultaneously from opposite ends, working off nothing but the steel grid itself and a safety harness 300 meters above open water. There was no elevator to that height yet, no scaffolding wrapping the building, just the exposed frame and the men climbing it. One of the most visually striking elements of the entire building extends from this exoskeleton, the Al Muntaha structure, a cantilevered arm reaching 27 meters out from the building's south face, roughly 200 meters above the sea, built bolt by bolt with nothing underneath it but air and water. Every one of those bolts would eventually carry the weight of a restaurant, a working kitchen, and the guests inside it, engineered deliberately over strength, because when you're hanging a room over open water, probably fine isn't a design philosophy anyone accepts. Above that sits the helipad, a circular deck at roughly 210 meters, built out from a ring girder with radial steel beams bolted into place one at a time, workers standing on a deck with nothing beneath it but the gulf. It's the same helipad that would later become famous for hosting a tennis match between Andre Agassi and Roger Federer, and a golf tee-off from Tiger Woods. Publicity stunts that only worked because years earlier iron workers had bolted that platform together piece by piece in open air. By the time the last major steel panel was lifted into place near the top of the frame, the building had its full skeletal shape. Still bare metal, still waiting for the one material that would actually make it look like a sail. Part 7. The sail itself. The fabric that gives the Burj Al Arab its famous profile is a Teflon-coated woven fiberglass membrane, PTFE coated on both sides, chosen specifically because it needed to survive decades of direct Gulf sun, salt spray, and summer heat well above 100 degrees Fahrenheit without degrading. Because the exoskeleton curves, no two fabric panels were identical. Each one was cut to match the exact geometry of the steel grid at that specific point on the building, with reinforced edge fittings crimped on to carry the tension load once the panel was stretched taut across the frame. When the first panel finally went up on the scaffold, it was, quite literally, the first piece of the sail ever installed on the sail-shaped building. The moment where a 3-year-old sketch by Tom Wright started to become physically real. Turnbuckles at each corner pulled the fabric drum tight, and for the first time, the building actually looked the way it had looked on paper back in 1993. 12 additional membrane panels were installed inside the atrium opening, each one a double layer, individually tensioned, oriented specifically to block direct sunlight from flooding the building's interior. Every panel, inside and out, was checked by hand. Crews tapped the surface, listening for slack, because a loose panel flutters in Gulf wind, and a fluttering panel doesn't survive a year of that kind of repeated stress. Joints between panels were sealed to keep salt-laden air from reaching and slowly corroding the steel behind the fabric. This is also where the building's double life as both a daytime and nighttime icon comes from. In direct sunlight, the Teflon fabric glows almost white. At night, with the interior lit, that same fabric becomes a screen, the entire building turns into a lantern visible for miles along the coast. That wasn't an accidental side effect, it was the design intent from the very beginning. One material doing two completely different jobs, depending on the time of day. By the time the final panels were tensioned near the top of the mast, 300 meters above the water, the building finally matched the sketch that had started this entire project 6 years earlier. Part 8. Building the inside of a legend. With the exterior essentially complete, the interior fit-out began, and this is where the Burj Al Arab's reputation for extravagance really comes from, though even here the actual construction process is more interesting than the finished marble suggests. Inside the building's hollow core sits what was, at the time, one of the tallest atriums in the world, roughly 180 meters of open interior space, lined floor to ceiling with 22-karat gold leaf applied one column at a time, pressed on with a brush because the material was too thin and delicate to handle with bare fingers. Carrara marble covers the lobby level with veining patterns matched slab to slab, so the natural stone pattern lines up seamlessly across every joint. A level of manual matching that has nothing to do with automation and everything to do with the stonemason eyeballing rock grain before the adhesive sets. The hotel's 202 suites are all duplex, double-height rooms, each with curved ceiling panels that were prefabricated off-site and then hung individually. And because the building's curve changes slightly at every level, no two ceiling panels are actually identical. One detail that rarely makes it into the highlight reels, the massive aquarium wall panels built into the property, made of 18 cm thick acrylic, each section engineered to hold back nearly 1 million liters of water pressure. Custom carpet shipped from South Africa and India were cut and fitted by hand for every single corridor, meaning that, technically, no two hallways in the entire hotel are carpeted identically. Chandeliers imported from the United Kingdom were raised into position by hand winch, with every electrical connection made from scaffolding suspended above the fixture. Brazilian green marble lines the royal suite bathrooms, held in place while the adhesive cured veining matched joint to joint the same way the lobby stone was. Nearly 1,800 square meters of 24-karat gold leaf went up across the property, applied one small sheet at a time, each piece roughly the size of a postage stamp. Even the mosaic work carries specific cultural weight, patterns based on traditional Arab astronomical designs, laid tile by tile from a full-scale template rather than a repeating stamped pattern. Up at the Al Muntaha restaurant, the one hanging 200 meters over the gull on that cantilevered arm, the entire kitchen had to be craned in through an opening in the structure and bolted down piece by piece, because at that height over open water, nothing in a working kitchen can be allowed to shift. Part 9. Testing a building that can't fail. Before any guest ever set foot inside, the building went through a punishing round of commissioning, engineering speak for making absolutely sure every system actually works before anyone's life depends on it. Glass elevator cabs were installed and run through their full vertical travel, lobby to top floor, over and over before a single passenger was allowed to ride one. The atrium's centerpiece fountain, which shoots water roughly 42 meters straight up inside that gold-lined space, was tested and recalibrated repeatedly until it hit the exact height the designers wanted. The private bridge connecting the island to the mainland, the only way in or out by land, grew span by span until it finally linked this artificial island to the rest of Dubai for the first time since construction began. Mechanical crews work floor by floor, testing every sprinkler head and every fire damper from the basement all the way to the top of the mast. The main electrical switchgear was energized and its protection relays tested before the building drew its first full load of power. The moment every system in the building was live simultaneously for the first time. Exterior lighting fixtures were mounted section by section along the exoskeleton and aimed individually from a barge floating in the gulf below. Then came the final cleaning, specialist crews rappelling down the full height of the sail face, top to bottom, washing away years of construction dust from a membrane that had to look pristine on opening day. A room-by-room snag inspection followed, with crews logging thousands of minor defects and tradesmen fixing them one at a time until the punch list hit 0. Part 10. The doors open December 1st, 1999. 5 years after that first pile went into open water off Jumeirah Beach, the Burj Al Arab opened its doors. The final numbers, 321 meters tall, sitting on 230 friction piles driven into an artificial island, supported by a single continuous pour of 70,000 cubic meters of concrete, wrapped in 9,000 tons of structural steel, all of it costing roughly $1 billion and requiring around 2,000 workers across 5 years of nearly continuous construction. It became almost immediately one of the most photographed hotels on the planet, recognizable in silhouette alone in a way very few buildings anywhere in the world can claim. Federer and Agassi would later play tennis on that helipad. Tiger Woods would tee off from the same spot. Guests would walk through a 180-meter atrium lined in gold and marble, standing directly above a concrete core that had been poured floor by floor back in 1996, long before any of the interior finishes existed. And underneath all of it, hidden from every photograph anyone has ever taken of the building, sit those 230 concrete piles and 70,000 tons of raft holding up the entire structure on ground that was open sea just a few years earlier. By the numbers. Before we close this out, it's worth putting the sheer scale of this project into terms that are easier to picture. 230 piles, each one 40 meters long, stack 4 of them end to end, and you're taller than most 50-story office towers, and that's just one single pile, driven straight down into sand with no bedrock to stop at. 70,000 cubic meters of concrete went into the raft foundation alone, poured in one continuous operation without a single planned stop. For scale, that's roughly enough concrete to pour a 2-lane highway more than 15 miles long, poured in this case into one slab underwater on an island that didn't exist a year earlier. 9,000 tons of structural steel make up the exoskeleton, heavier than the steel used in some mid-sized suspension bridges, bolted together piece by crews working without scaffolding 300 meters above the sea. 1,790 square meters of 24-karat gold leaf line the interior, applied one postage stamp size sheet at a time by hand. 202 duplex suites, each one double height, each one finished with curved ceiling panels that are, every single one, slightly different from the last because the building's curve changes subtly at every floor. And the timeline, 5 years start to finish for a project where the first 3 years were spent almost entirely underwater or on an island that hadn't been built yet, and the ground crew wouldn't set foot on solid land at the site until roughly a third of the total construction schedule had already passed. 2,000 workers, $1 billion, 0 existing land to start from. Dutch Sheikh Mohammed asked for a single image in 1993, something the world would recognize before it recognized Dubai itself. What he got 5 years and $1 billion later was exactly that, a building whose shape came first and whose city grew up around it afterward. Nearly everything people associate with Dubai's skyline today, the ambition, the scale, the willingness to build somewhere no one else would even attempt, traces back to this one project. Not the tallest building in the world, not the biggest, just the first one built on land that engineers had to invent before they could even start. The Burj Al Arab wasn't built on the coast of Dubai, it was built on nothing. And that's exactly why it's impossible to forget, why this still matters. Here's the thing that makes this project worth understanding. Almost 30 years later, nearly every impossible building that came after it in the Gulf owes something to what engineers figured out on this one site. The Palm Islands, built a decade later, a few miles down the same coastline, use lessons learned directly from this project's marine construction: how to place fill, how to compact it, how to protect an artificial coastline from wave energy over decades, not just years. The Burj Khalifa, which would eventually dwarf the Burj Al Arab in height, relied on foundation engineering that assumed deep piling and friction-based support were not just possible but reliable, something that hadn't been proven at this scale in the region before 1999. For an American audience, the closest historical parallel might be something like the construction of early Chicago skyscrapers in the 1880s. Engineers working with soil conditions nobody had built on before, inventing foundation techniques essentially in real time because no existing playbook applied. The difference here is that Chicago's builders were working with soft clay under a city. The Burj Al Arab's builders were working with open ocean. There's also a simpler reason this project keeps showing up in documentaries, engineering channels, and travel content almost 3 decades later. It's rare for a single building to function simultaneously as a hotel, a national symbol, and a genuine engineering case study. Most iconic buildings are one of those things. The Burj Al Arab, almost by accident, ended up being all three. A livable hotel that guests actually stay in, a piece of marketing that put an entire city on the map before it had much else to point to, and a foundation engineering problem that pushed marine construction techniques forward across an entire region. None of that happens without the part nobody photographs: the piles, the fill, the raft, the 3 years spent making land where there wasn't any. And